All right, so I want to talk about this little controller here. It's a $10 controller off of either Amazon or not Amazon. Maybe they have them on Amazon. I haven't checked. I'm an eBay and Aliexpress person. They seem to have gone up in price. A lot of them are charging shipping now. Of course, you get hit for tax now, but generally it's $10, $10, $12. You can get some that have a heat sink on the back of them, and I think they're only like $15. And I tell you what, I bought a heat sink separately, and it's expensive as hell. So let's see, we're going to measure the battery voltage. You see I've got 10 volts here, and the motor's running really well. Flip our little switch under here. Motor runs the opposite direction. So I think the only thing I'm going to do is go with the new battery pack here pretty soon. What I want to do is verify something that I have heard, that the we're talking about putting a heat sink on the back of it. If you drive this thing, if you're going to try to drive it at I believe they said over 65 watts, that you need a heat sink on the back of it. That what you're going to end up with, the problem with putting a heat sink on them, and that's why I'm considering buying one that already has a heat sink on it. The theory is that these don't have the same potential. A lot of times the heat sink, well, you see they have a voltage here. Okay, what do we got? We got 10 volts, 10 volts, 10 volts, and what's this doing? Going down. It's 0.50. So I mean, it's for all practical purposes, it's zero voltage here on this one. So this is a difference. You can't stick a heat sink on here without having them isolated. You need to have that material in between there. I want to say dielectric material, but that may be the wrong word off the top of my head. So you can see you need to make sure you have a good insulator there if you're going to put a heat sink on it, and that's why I think it's worth buying one with a heat sink. And like I said, I think they're more closer to $20 by the time you get tax and everything put in. So anyway, it works really good with these motors. My objective has and always will be building my own controller. But this is real nice to test the motor with. And it could actually be put into some kind of application as is. I'm going to disconnect this battery so I don't accidentally, you see how I got all my wires nice and covered up. The next motor hopefully will have a better wiring scheme on it. We'll see how I do. Okay, so this is a really nasty looking little schematic I've got here, but it will do what we need to do, because you've got a row of pins down this side. There are 6 up here at the top, and that's something else you have to pay attention to when you order this controller, because I've seen some of them that don't have the Hall connections, so they may not support censored motors. Okay, so these ones down here at the bottom, these 5 down here at the bottom, are for the Hall sensors. It's got a negative, and they're labeled pretty good. Here on the back you can see it says ground, and HA, HB, HC. So, and 5 volts, and it says Hall on there. And up here, these 6 up here at the top say set. Well, this is 5 volts. This is a 5 volt source. Also, I should go back here and say this Hall, ground, and 5 volts is a source also. So this 5 volts is connected to the VCC on the Halls, and the ground is connected to the ground on the Halls. And then ABC, we'll get into that in just a second. So this set has 5 volts and a ground, both of them at opposite ends. And the first one is EL. And that, I haven't tried it, but it says run is ground and VCC is stop. So I think if you had a switch here that switched from ground to the 5 volts, I think when you switch it to 5 volts, it'd turn off the motor. And I believe that would work for a brake situation where you want to stop the motor whenever you hit the brake, like if you have it on a bicycle or a vehicle of some kind. You wouldn't want the motor to keep running if you put on the brake. So you want the brake lever to hit a button and turn it off. It's counterintuitive, but that's the way it goes. And the next one is signal. And that signal puts out a pulse. And so I'm assuming that you could take those pulses and run them to a tachometer of sorts, run them to your Arduino or something to make a little display for your tachometer. Okay, so then the next one is ZF, and it says it on there, ZF, and forward is ground and backwards is VCC. Well, I guess that depends on your perspective. One way's forward and one way's ground. You can see one way's forward and one way's reverse. And you can see my little switch I have connected to that. I have it center to the ZF, and one side going to negative and one side going to positive. And just depending on which way I have it set determines the direction of the motor. And I haven't seen any difference in performance. I don't think there really would be. That's a technical issue about the way the software handles the Halls. It reverses. Anyway. Then next you have the VR, which is next to the ground, which have it running into the center of a 10K potentiometer, and one side goes to ground, one side goes to 5 volts, and it adjusts the speed of the motor, which would be the modulation on the excuse me, on the transistors here, the power transistors. Okay, on this side you have the voltage in, which maximum is supposed to be 36 volts. I burnt the last one up running on 36 volts, but I was using a different motor that I don't think was as good as this motor. I've tried 15 volts on this, and that worked really well. And I might try something a little higher here later. But so you can see this first pin says P plus, that's your input voltage, and P minus, the negative. And you saw I had them connected up to the battery. This has a regulator on it to bring down to the 5 volts for the system, the set and the Halls. And then it's got the shunt and all these caps that go for the MOSFETs to run the motor. So you have your positive and your negative, and then you have it says M, C, MB, MA. So you have A, B, and C. Okay, so you noticed also on the hulls you have A, B, and C. So what you want to do is determine which direction you're going to call A, B, and C. So I've got A, B, C, and I look at my coils and I make sure I'm going A, B, C with those also in the same direction of rotation, so I don't flip them. Well, I saw on another video a guy say that if you have the hulls wrong, that you can burn it up. And I don't think I had my hulls wrong on the other motor. That's another story altogether. These hulls are mounted where they fall in the center, in between the magnets. You can see the magnets there rotating, and you can see it's right in the center, in between, well, in the center of the magnet, you can see. And so then it'll flip, the polarization will flip as it goes past. So it's perfectly aligned, but it's let me say one more thing, that the coils, it's also in between the coils. If you could see that, you'd see it's in between the coils. It's not centered on the coils. And I ran my very first motor with the Hall sensors in the center of the coils, and it worked great. But again, I think that one of the issues is that this is a, what can I say, a minimalist motor. Only 3 coils and 4 magnets. I think that's another story altogether. I'm getting off track. I wanted to talk about this here. And I think that pretty much covers it. You can find much better schematics online. I should probably put a link to one of the eBay controllers that has a nice picture of it. I've got a picture. I don't know where I got it from. I think I got it off one of the eBays. And that should work. I think that is, I hate to say it, I think I gave the best explanation of all the pins, because I had trouble following a lot of the guys online. So that's it for now, and I hope this helps.